I wrote these examples up for you guys. Let's try to go through them now. Find a longer piece of chalk. If I try to write too long with a little nub, it hurts my hand. Man, I keep forgetting to bring new chalk from home. All I got is nubs. It's gonna be a bad day. Okay, so the first one. Oh, I could use green. That's what I could do. All right. So the first one, f prime of x, 2x minus 2b, right? Set that equal to 0, we get 2x equals to 2b, so we get x equals to b. It's a critical point. Then f prime prime of x is equal to 2, which is greater than 0. Therefore, f of b is local minimum by second derivative test. There you go. Second one, this is on the next page in the notes, by the way, will require a little bit more thought. So, but the first step is the same. We got to find the critical points. So, df dx is what? So by the chain rule, we have minus 2x e to the minus x squared. We want to set that equal to 0 to look for critical points, right? Well, this is e to the x is non-zero, right? E to the minus x squared is also non-zero. So the only way this can be 0 is for x equal to 0. So x equal to 0, this is the only critical point. So I can already draw my number line here for df dx, right? And what's the story? If you plug in a negative number, you get a what? You get minus 2 times the negative number times the exponential. Well, the exponential is positive, so we got negative times negative, it's positive. So the derivative is positive to the left of 0. And if you plug in like x equals to 1, you get minus 2 e to the minus 1. So that's negative. So thus, f increasing on minus infinity to 0, and f decreasing on 0 to infinity. All right? So we've answered, increase and decrease, right? And also, you can already tell me what are the extremal points. Only extreme point is 0, comma f of 0, which by the way is equal to 0, comma 1, right? Because e to 0 is 1. Is that a local max or min? Well, look at the sign chart. By the first derivative test, we're going up, we're going down again, which is local, which is local maximum. I should say is at, fine, at a local maximum. You could say is a local maximum, I don't really care that much. All right, what's up next? Concavity, right? Concavity. So f prime prime of x, what's that equal to? That's d dx of the first derivative, right? That's d dx of minus 2x e to the minus x squared. So this time I have to do the product rule, because it's a product. And the product rule here gives me minus 2 e to the minus x squared minus 2x times minus 2x e to the minus x squared. So we have to differentiate e to the minus x squared again, just like we did for the first derivative. And you don't want to leave it like that. You want to clean up your work because otherwise it's hard to see where it's 0, right? So I'll suffer the nub. All right, so we've got minus 2 plus 4x squared times e to the minus x squared for f prime prime. See that? 2x minus 2x times minus 2x is a plus 4x squared, and you got the minus 2 there, right? So this says f prime prime of x equals to 0 if and only if what? If and only if minus 2 plus 4x squared is equal to 0, which is true only if x squared is equal to 1/2, right? Which is true x is equal to plus or minus 1 over the square root of 2. So those are my possible points of inflection. Draw a number line, for f prime prime. I'll put in my points of interest, minus 1 over root 2, and 1 over root 2, right? By the way, this is about 0.707 numerically, right? For what it's worth. I mean, it's worth us having a better sketch on the graph. That's what it's worth. So, all right, you look at the formula for the second derivative, and you plug in a number, right? So I'll plug in 0. Plug in 0, I get a negative. So it's negative up in here. And if you check points on the other side, you'll get it's positive over here and over here. All right, so basically it's concave down up in here, it's concave up in there, it's concave up over here. I mean, you could write that on the number line just the same. You could say, oh, this is increasing, this is decreasing. That's fine, but I almost always ask you to give me the answers in interval notation. So if you just write increasing and decreasing on the number line, that's nice, but it's not the answer. I insist on you giving the answers in interval notation because a sizable percentage of the students here need to work on interval notation. Anyway, so concave up on minus infinity to minus 1 over root 2, and 1 over root 2 to infinity, and it's concave down on minus 1 over root 2 to 1 over root 2, right? So thus, plus or minus 1 over root 2, comma, f of plus or minus 1 over root 2 are points of inflection, right? Now, what happens? Let's work it out. What is f of plus or minus 1 over root 2? How's that go? E exponential, right? Of minus parentheses plus or minus 1 over root 2 squared, right? So the square is just on that term. So when you square plus or minus 1 over root 2, you get a half. Either way, you get a half. Because square root 2 squared is 2, so that gives you a half. So we're just left with e to the minus 1/2, right? All right, and I'll crunch a number there just for the sake of specificity, if you will. See here, e, oops, that's log, I don't want log. E to the 0.5, what have I got? Oh, minus 0.5, very careful. Minus 0.5, right? So this is approximately equal to 0.606, all right? So here's the graph. We've got a local maximum at 1. So 0, 1, there's your local max. In fact, in truth, that's a global max. And over here, let's see, so it's 0.5. So let's do that 0.5. 5, right? So let's see here. What's going on? What happens to what happens to y equals e to the minus x squared? If you think about this function, what happens as x goes to a very large positive or negative number? You've got an exponential of a very large negative number either way you go. So what I'm saying is that this function goes to 0 as x goes to infinity. So you got these horizontal asymptotes that it's tending to way on out, you know? Like I know it's eventually going to get closer and closer to 0. So the sort of the tail behavior, something like that, you know? And then what's going on is when it gets to minus 1 over root 2, or plus 1 over root 2, right? Which is about minus plus or minus 0.07. Right there, wherever that is, oh, I know where it is, it's 0.606, so it's like up here, right? Roughly speaking. Above the halfway mark, right? Right there, the graph is changing from being concave up shaped, right? To what? Concave down, right? So that's the point of inflection. So it turns over there, concave up. Shoots to concave down, like that. And so right here, and right here, these guys, points of inflection, right? Local, in fact, global max. Sorry, I used green for my labeling, but anyway. So there you go. This is the, this is a rather famous curve. You guys know what this is called? This is called the bell curve. Or also, in more mathematical circles, it's a Gaussian. So these have tremendous application in probability theory. Not this one, but they're often rescaled so that the area under them is equal to 1, and they represent what's called a probability distribution. A wide variety of statistical problems have a distribution that looks like this. There's a lot of people close to the middle, and then there's just a few people way out on the tails of things, you know. You guys ever listen to Jordan Peterson? Look at he's a, whatchamacallit, one of them people that thinks about the human brain.
Psychologist?
He's a psychologist, yeah. And he talks a lot about the tails, he talks a lot about the tails of distributions and trying to help people understand why there's more of a particular type of person doing a particular type of thing. But anyway. All right, next example here. This is probably gonna be our last example of graphing, okay? They just take so long, but here's f of x equal to 3x to the 5th minus 20x to the 4th plus 40x cubed. And we're supposed to find the intervals of concavity, increase and decrease. Same instructions as the last example, all right? So what do? Let me just stop and say what we do. We find critical points. We find where the derivative is 0. Then we find where the second derivative is 0. We draw a sign chart for both of them, you know? And from that we can cipher where it's increasing, decreasing, concave up, concave down, and the rest. So I'm just going to dive right into this and just calculate the first derivative. That is 15x to the 4th minus 80x cubed plus 120x squared. And I'm going to calculate the second derivative. While I'm at it, 60x cubed minus 240x squared plus 240x, right? So there it is. There's the calculus that underlies this problem. And so when's f prime of x equal to 0? Well, we've got what? X squared times 15x squared minus 80x plus 120. Why have I done this to myself? Can you guys factor that? Let's factor 5 out. 5x squared times 3x squared. What's 5 goes into 80? How many times? What? 16? 16x. Divide 120 by 5, what do we got?
24.
24. Pretty good. Well, I can complete the square here. Maybe I can just factor it. Let me try. I'm being an optimist. I don't remember how I made up this example. So odds of this working out are somewhat slim. I need a minus 16 in the middle, right? Which means 24 has got to be achieved as a product of negative numbers. I'm guessing 6 and 4 is what I used, rather minus 6 and minus 4. If I use those, can I make that work?
You use 8.
8 and 3, minus 3 and 8. How would you? Maybe, say minus 3 over here and minus 8 there. That gives me minus 9x minus 8x. 17. Curses, that's so close. So close. 12 and 2. Minus 12 and 2. I mean, 24 is such a horrible number for factoring, isn't it? So many choices. If I do 12 and 2, that might do it. No, that's going to give me like an 18, isn't it? Right? That gives me a minus 8. So we got 17, we got 18, but 16, it's mocking us, isn't it? All right, I gotta take my medicine. Take my medicine. Here he goes. So I do factor out the 3, and then I've got x squared minus 16 thirds, x plus 8, right? Complete the square. So I'll bring that's 15. So I've got x plus 8 thirds, or rather minus 8 thirds, squared, minus 64 over 9, plus 8. But 8 we should rewrite as, in terms of ninths. And let's see, 8 times 9 is 72, 72 minus 64 is 8. So we've actually got plus, oh, look at that. Look at all that. You jerk. Look what I did to us. So all of that to find out what? Never 0, right? So this quadratic that we have factored out is an irreducible. It does not produce a 0 because it's a sum of square. I mean, it's a sum of two positive things. It can't be negative. Do you guys know a simpler way you could have seen this without going through all this? You could have checked the discriminant, right? B squared minus 4ac. Here would have been 16. Well, pick whichever one you want. We'll pick this one. So it would have been like 16 squared minus 4 times 3 times 24, right? And 16 squared, what's that?
30.
It's 160 plus 6 times 6, right? 6 times 16? Wait, is that right? 6 times 16 is 96. 256, I think 256, yeah. So 256 minus 12 times 24, what's 12 times 24? That's 10 times 24.
280.
What's that?
Is it 288?
88? Yeah, 288. So the point is,
You'd get a negative.
this is less than 0, therefore that polynomial is irreducible. You know, we could check discriminants if we're kind of like, if you run into factoring which isn't going well, it is a good investment of your time to take a second to calculate the discriminant, because if it works out to be negative, you know that cannot be factored over the reals, right? No zeros from that. Okay, so anyway, algebra done. That was the whole point of this example, actually, was to review this. Now we've done it, great. So f prime of 0 equals to 0 only for what? X equals to 0. X equal to 0 is the sole critical number here from this, right? And so you can make your sign chart. You got your 0, and if you plug in, the thing is, if you plug in a negative number, it's positive. If you plug in a positive number, it's positive. So here, 0 is a critical number, but it's not a local max or min by the first derivative test. It's neither max nor min. Oh, goodness. Chalk is getting to me. All right, so how about the concavity? What do we need to figure out there? So this is increasing on minus infinity to 0 and 0 to infinity. In fact, you could really just say it's increasing everywhere. You wouldn't be wrong. Anyway, f prime prime is what? We can factor 60 out, right? 60x cubed minus what? 4x squared plus what? 4x, right? Hopefully this one goes a little bit nicer, yeah? Here we've got 60 x squared. We can factor x out. Aha! That factors. That is 60x times x minus 2 quantity squared. Thankfully, we don't need to complete the square or anything too fancy here, right? It's a basic factoring problem. But, so you see then, we can make our sign chart, our prime of x. We have possible points of inflection at 0 and at 2, right? There's a professor somewhere out there who was annoyed that these kind of points didn't have a formal name. Like we call places where the derivative is 0 critical points or critical numbers, but there really is no standard name for possible points of inflection. Most people don't say possible points of inflection because it's annoying to keep saying that. It's a lot to say. So he just named them after his last name, like Hergman or something like that. I can't remember. It's very silly. And there's all kinds of people with T-shirts, you know, taking selfies of themselves with their shirt with the number. Anyway, it's a thing. Math folklore aside, we need to pick a point in each subregion. If we pick a negative number, like over here, you get a negative times a positive, so you get a negative. If you pick a number between 0 and 2, you've got like 1, for example. Plug in 1, you get a positive. And then plug something in like 3, you still get positive times positive. See, so I said last time in passing that if the factors were linear, it flips signs on the sign chart. Here's an example of like an even power where it doesn't flip sign. So as a rule of thumb, you should see sign flips when there's a factor that's even. It's going to be odd, but if the factor is even, it doesn't flip sign. Anyway, so here it is. Concave down, on minus infinity to 0, concave up, on 0 to 2, and 2 to infinity, right? Where's the inflection point?
0.
at 0, comma what? The y coordinate for the inflection point easier to find this time, right? 0.
0, 0.
It's 0, 0, right? So if you plug in 0, f of 0 is 0.
Mm.
There's no constant term, right? So the y-intercept is 0. All right, now we can graph. Or we can try to graph. Let's see here, what do I know? It's got a local... So first of all, by the way, sidebar, this thing like globally looks like this. That's the big scale picture. It's an odd power, so it looks like, roughly speaking, an exaggerated cubic since it's the 5th power. And it looks like that because it's got a leading coefficient which is positive. That's the large scale behavioral graph. This we know, hopefully, from our previous experience graphing in like pre-calc or whatever. Now, what else do I know? 0 is a point of inflection. And let's see here. Shush. Ah, that's right. One of my previous. Yes, please. One of my. Shush. So one of my previous students is now getting to the end of grad school, and he's.
You like Star Wars?
He's yeah, like Star Wars. I used to like Star Wars. Yes and no.
You like the older movies?
Yeah, I like Star Wars before it's corrupted.
Yeah. Disney.
There are some recent things I like Rogue One, fantastic. Mandalorian, great.
Yeah.
The recent trilogy, a dumpster fire. So,
Trash, yeah.
yeah, just trash. Anyway, so, I mean, it's got beautiful cinematography and better acting than the prequels, sure, but in terms of writing, absolute dumpster fire. Anyway, so concave down, up to the origin, and then it turns up, right? And something funny happens at 2. I'm not sure exactly how to graph that, but basically this is the best I can do with what I've got. That's the graph. So. Now you can improve this, of course, by doing what? What can you always do to improve a sketch of a graph? You can plug in a number and figure out the specific y value for that point. And if you add like 2 of those, one on each side, you can vastly improve the quality of the graph, right? By setting the scale of like where it is at -2, where is it at 2, you know? I can improve the graph that way. I'm not going to. This is just a sketch. Okay, so that's it. Just to reiterate, graphing is a many-step process, right? First, got to find the critical points. Second, we got to find, the second derivative and find the possible points of inflection. We got to make a sign chart for each, come to an account of where it's positive and where it's negative. That tells us intervals of increase and decrease, and then we can rely on like first derivative test or second derivative test to decide, like, is it a local max, local min at the points where the critical numbers are. And then after all of that, and you find the points of inflection, right? After all of that, you come back and say, I want to make a graph, right? So you still have to fall back on your basic pre-calculus stuff, like what's a y-intercept, can you see any x-intercepts, all that stuff is still there, right? But you take that and you can improve on it because you know where local maxes and mins are with calculus. The only thing you could find a local max or min for in pre-calculus was a quadratic. That is the only function that we have like stone-cold formulas for the min or max. We find the vertex of the parabola, right? That's either the minimum or the maximum. Well, now we can find mins and maxes for all kinds of stuff in all kinds of places, We don't have general formulas for them, but we can find them for specific examples, all right? Okay, so that brings us to our sort of final mathematical tool for understanding questions of maximization or minimization, as it might be. And this is a very simple thing, actually, closed interval test. So don't miss this one. I always ask a question about this on the next test. There's really no reason to get it wrong. It's actually even easier than what we've been doing. And the closed interval test simply says, given continuous, that's important. Continuous, trying to spell continuous. F of x on the closed interval from A to B. Step number 1, find f of A and f of B. All right, number 2, find all critical numbers C inside the open interval from A to B. All right, so what does that mean? It means either f prime of C equals to 0 or f prime of C does not exist, right? And step 3, calculate f of C for all C found in step, in step 2, right? Here's step 4. Step 4, select min and max from numbers in 1 and 3. That's it. And the closed interval test says that when you get to step 4, one of these numbers will be the minimum, one of these numbers will be the maximum. Excuse me, let me clarify my language. At least one. You can attain the minimum and the maximum more than 1 point, of course. I'll give you guys a second to digest that. Start with a really simple example. So f of x equals absolute value of x on, let's say, minus 3 to 2. So is absolute value of x continuous? Sure it is, all right. And what's the derivative of absolute value of x? Well, that's d dx of the square root of x squared. See, that's a formula. Well, okay, let me I've gone through this before, so let me not go through this again today because we're a little bit short on time. We worked this out before. The absolute value of x, it's either minus 1 for x less than 0, or it's 1 for x greater than 0, right? And f prime of 0 is not defined, right? So that's the derivative. It's either minus 1, because the absolute value function, what's it look like? It's like a v, right? So it's like either slope minus 1 for negative or slope 1 for positive. That's it. And at 0, there's a kink in the graph, so the tangent's not defined there. All right, so I'm not following my own algorithm, my bad. So number 1, what's f of minus 3, absolute value minus 3, 3, right? And f of 2, absolute value 2, also known as 2, right? So I have achieved step 1. Step 2, from the calculation I just did, c equals to 0, only critical number, right? Step 3, f of 0, absolute value of 0, is 0. So what's the min and what's the max? Thus, by closed interval test, f of x equals absolute value of x has f of 0 equals to 0 minimum on minus 3 to 2, and it has f of, what is it, minus 3 equals to 3 maximum on this closed interval. These results are completely unsurprising because if we graph this, what's it look like? Absolute value of x minus 3 to 2 Right, so you can literally see that this result makes total sense, right? because 3 is the biggest that the absolute value gets, and 0 is the smallest. But the nice thing is that we can, sorry to people at home, I have forgotten to move the camera over here. The nice thing is, of course, that it just, all you gotta do is check the values at the endpoints and any critical numbers, and there it is, right? No need to use the first derivative test or anything like that. You just check cases. Let's see here. I'll do another example. This is the f of x, x to the fourth, I may regret this, minus 2x squared plus 3 on 0 to 2. All right, so I'll try to follow my algorithm this time. So step number 1, let's calculate the value on the endpoints. So f of 0 is what? 3. F of 2, well, it's 16 minus 2 times 4, which is 8, plus 3. So that looks like 11, right? So we got 11, and we got a 3 at the endpoints. Step number 2, I calculate the derivative, which is 4x cubed minus 4x. Ooh, that's not too bad. So that's 4x times x squared minus 1, which is 4x times x minus 1 times x plus 1. So the derivative here straight up factors, and it shows me that I've got critical numbers, you know, c equals to 0, 1, and minus 1. Those are my critical numbers. So step 3, I should calculate what's f of 0, what's f of minus 1, what's f of 1. Sorry. I made a poor choice. I should have erased and worked over there for you.
What?
And I should have worked up in the format way you move. Although getting up and moving around is
What
helpful.
dice is this?
What's that?
What dice is that?
Oh, that's a good question. It is on page 157. It is 5.2.4. Thank you. Now f of 0 we already calculated. We already know that that's 3, right? So it so happens that the endpoint is also a critical point for this function, which is kind of cool. Minus 1. Well, that's easy to plug in, right? Minus 1 to the fourth is 1. And minus 1 squared is 1. So what you got is 1 minus 2 plus 3. We plug it in, right? 1 minus 2 plus 3, what's that equal to? 2, right? And we plug in 1, we also get 2. Because that's an even function, so it's going to be equal for plus or minus 1. All right, so what's the, let me circle all of our possible winners and losers with a colored chalk here. So 3 is a possible winner and loser, 11 is a possibility, 3 is a possibility, we already got 3, but anyway, 2 or 2. So you look at all those, the minimum and the maximum must be attained in there. So what's the min, what's the max? Maximum f of 2 equals to 11 is max f of x on 0 to 2. And what's the minimum? It looks like the minimum value is 2, right? We found that 2 different places, right? F of minus 1 equals f of 1 equals to 2 is minimum value for f of x on 0 to 2. So in this case, you know, yeah. So there you go. That's the closed interval test. It's kind of relaxing and simple compared to the other examples we did today, right? Like the graphing examples really require a lot more continued attention, don't they? And that's the end of my chapter 5, all right? So chapter 5 was on geometry and differential calculus. I've shared with you,
Hold on.
the major tools that we have to work with. There's one other we'll study in the lab tomorrow called Taylor's theorem. I already kind of hinted at what that was in an earlier lecture, but we're going to dive into that in the lab tomorrow. You'll really see it a little better. And since I'll actually be here to do the lab with you, it should be like, maybe we'll have slightly better participation than last time. Anyway, okay, so the next topics are optimization. I think I have a chapter I devoted to optimization. So what is optimization? Well, optimization is just applying, nothing more than just applying the techniques that we've been looking at to specific word problems. It's just that. I could show you a specific example of this. It's kind of a silly example, but here it is. Range, right? The range of a bullet with speed v naught at angle theta, and neglecting friction, air friction, given by r is equal to v naught squared sine of 2 theta over g. Right? This is the range equation that you learn in physics. So you can ask the question, okay, what's the maximum? What's the maximum range? What angle should I choose for maximum range, right? And I say this is a silly example because you can solve it with pre-calculus. If you have a solid understanding of sine, you should immediately tell me, oh, that should just be whatever makes sine 1. So the answer is obviously pi over 4, right? But let me show you how we do it with calculus. So the calculus solution says, okay, so you're going to look for the critical angle. The v naught squared and the g, these are physical constants, the speed and gravity, right? And we're calculating dd theta of sine 2 theta. Well, you know how to do that. Chain rule, we get 2 v naught squared over g cosine of 2 theta, right? And we have to set that equal to 0 for our critical angle. Now, for physical reasons, right, the angle theta, we should really take to be between 0 and 90, right? We're just going to, for our convenience, we're assuming we're shooting the gun that way, right? I don't advise shooting the gun at 90 degrees, it's always something to avoid. But, man, there used to be this Taco Bell commercial where they shot the bullets straight up in the air. And like the whole commercial, and then like at the very, like towards the end of the commercial, all of a sudden they're like, the bullets, and then they all go running, and then all the bullets just like rain down. Taco Bell used to make way better commercials. You guys just don't even know. Before you were born, probably. Yeah, Taco Bell. Let's see here. So this just means that cosine of 2 theta is equal to 0, right? Now, if 2 theta is equal to 0, and theta is between 0 and 90 degrees, notice 0 is less than 2 theta is less than 180 degrees, right? So if you think about 0 to 180, this is like 180, right? The only place where it's 0 is 90 degrees. So this means that 2 theta must be equal to 90 degrees. Or if you want, you could use, I really should, excuse me, this is calculus, I should really say pi over 2, right? Radians, so theta is pi over 4 radians, which of course is equal to 45 degrees as I claimed. So the max range you obtain from 45 degrees. However, I should comment, this has assumptions. The range equation assumes that you're starting and ending at the same altitude. All right? If, on the other hand, you know, I'm not going to get into this because this is not a physics course, but I should tell you, if you're shooting a cannon off the top of a building, right, it is no longer the case that 45 degrees maximizes the range, because the range equation no longer applies. I mean, I can work through it if you'd like. If this height is h, right, then your equations that you have to solve are x equals to, well, we'll make this x equal to 0 for convenience. So x is equal to, and suppose this goes to v naught. Well, you look at the angle theta, the initial x part of it is v naught cosine theta. The initial y part of it is v naught sine theta. This leads to the kinematic equations v naught cosine theta times time. And in the x, we're assuming no air friction, so that's it. Like, it's just velocity times time gives you the x coordinate. There's no acceleration in the x. In contrast, in y, we have the initial y, which is h, and then plus v naught sine theta times t, and then minus 1/2 gt squared, right? So to find this over here, this is what you want, x of t, you know, star, what do you want to call this, the time when it hits back to the ground. What do you have? What characterizes that? Well, what characterizes that is that y of that time is 0, right? So to figure out that time, you have to set this equal to 0. You have to solve that quadratic equation. All right? And so I can multiply this by g over 2, I get t squared. I'm going to multiply this by minus g over 2, I get t squared minus 2 v naught sine theta over g t minus 2h over g equal to 0. Complete the square on this, you get t minus v naught sine theta. This is definitely violent. I'm sorry. I said I didn't have enough time today. Why am I doing this? I'm an idiot. But it's too late. What's done is done. I have to finish this. It's v naught squared. My apologies. But I'm still going to finish it. G squared minus 2h over g. Right? Which then gives you, moving to the other side, t minus v naught sine theta over g is equal to plus or minus the square root of 2h over g. I feel like I lost a minus. Well, this was supposed to be minus. Completing the square, I have to subtract off that thing. So, but when I bring it to the other side, they both become plus. Right? And so then, if you'll allow me this sleight of hand with the chalk, I can rewrite this as equals plus or minus that thing, right? Now, one of those times is positive, one of those times is negative. The reason one of those times is negative is that these equations are symmetric in time. So if you follow this back, one of the times is going to give you that. Let's say that this is t plus minus, this is t minus, this is t minus. On the other hand, t plus is the t star, right? And the equation for the range is literally r equals to v naught cosine theta times t plus. Well, that is v naught sine theta over g, right? And plus or minus, I think I'm missing a 2. Oh, I'm not missing a 2. Never mind. Well, I just remembered. Plus, right? Plus the square root of this stuff. So what happens when h is equal to 0? You guys see it? Physics is so much harder than math. By the way, physics is much harder than math. Do you know that? This is a relatively simple physics example. See what happens when h is equal to 0? You get square root of this thing squared, but that's exactly this term again. So you add them together, you get 2 cosine theta sine theta from that, right? But remember, there's a trig identity that this is equal to the sine of 2 theta, which is why we get this formula, the standard range equation. So you can see that this derivation drops back to the standard range equation in the case h equals to 0. In the case h is not equal to 0, to find the maximum range, consider this. You have to differentiate this with respect to theta and see where it's 0. For a specific choice of h, that is a formidable problem. Like, I always have to use a numerical technique to actually find the angle when I put numbers in, all right? Like, when I taught physics, I mean, this is a problem I would regularly assign. It's just really difficult. And I think it ends up being, you need like an angle higher than 45 degrees. Well, usually there are 2 angles, if I remember right, that'll work. But anyway, so sorry, I wasted much of our class time on that. But maybe you guys like to see this sort of thing on occasion, I don't know. But you know, to apply the calculus, I mean, you really can use what we're doing to answer very interesting questions. It's just very interesting questions also come with the cost of very difficult calculus. So like when I differentiate this with respect to theta, I see it's much, much more of a pain, all right? But that in a nutshell is optimization. We take a word problem and we apply methods of chapter 5 to decide which is biggest and smallest for the problem, right? We'll work more of those probably Thursday, all right? Or if there's a specific one you have a question about, we can talk about it. But I need to move on to the final topic for today. And the final topic for today is what's called L'Hopital's rule, which looks like the hospital rule. And I don't seem to find any consensus on the spelling of this, so I'm just going to call it L'Hopital's rule. I'm going to write it like I pronounce it, L'Hopital's rule. And L'Hopital's rule says the following. It says that if the limit of f equals the limit of g equals to plus or minus infinity or 0, then the limit of f over g is equal to the limit of f prime over g prime. Now, and here I'm being very vague by writing, but when I write lim, like this, without adornment, without decoration, I mean to include all the different possible cases. Limit as it goes to the right, limit as it goes to the left, the double-sided limit, the limit at plus infinity, the limit at minus infinity, all of those. All right, so like, I'll start with a really nice example. Limit as x goes to 0 of the sine of x over x. All right, so this, notice the limit as x goes to 0 of sine x is what? 0. The limit as x goes to 0 of x, 0. So we can apply L'Hopital's rule. And here's my notation for it, by the way, guys. So L'Hopital's rule, type 0 over 0. So you got 2 options. You can either use my notation, which was shown to me by a calculus professor when I took calculus 2, all right? The L is for L'Hopital's rule, and then under it I write the logic for it, 0 over 0. I cannot produce this in my notes, by the way. I don't know how to LaTeX this. It's beyond my skills. And I've never seen anybody properly implement it yet. But this is a standard notation. So what's the derivative of sine? Cosine. What's the derivative of x? It's 1. Bam. We're done. Because cosine of 0 is 1, right? So this is just cosine of 0 over 1, also known as 1. So with L'Hopital's rule, we can derive the limit of sine x over x is 1. Now before I proved that using you know, somewhat circuitous geometric arguments. We looked at a unit circle, we, you know, squeezed the graph of sine between two other things, I believe. Let's see here. Now, at this point in the course, it would be wise to go back and look. There's like a thing I skipped over in the limits chapter, the limits at plus or minus infinity. You might want to go back and look at that now. I'll try to send you guys an announcement later with a specific reference, because I don't seem to have the page printed out in front of me at the moment, but there's a particular, like, 2 pages in the earlier limits chapter I skipped over, because like, time is short at the moment, and I just skipped it. But now, you should look through it just so you like, refresh your memory about limits at infinity, plus or minus infinity, because we also do examples like that. Let me show you one. So suppose we have a limit as x goes to infinity of, let's say, 3x squared plus 2x plus 1 divided by 7x squared minus 3. So as x goes to infinity, how do you judge what a polynomial does as x goes to infinity? It's completely governed by the leading term. If you think about it, once you get to like 1 billion, think about 1 billion. If I square 1 billion, how big is that? Like it's beyond the national like budget, right? It's big. Maybe even beyond the deficit. I don't remember. Anyway, thinking about minting $1 trillion coins, like what? Really? Anyway, so if you think about 1 billion, like 1 billion squared is ginormous, and then you got like 2 billion. So these next to leading, the ones that aren't the leading terms, are irrelevant as you think about x going to infinity. All that matters is the biggest guy on the block, the 3x squared, the 7x squared. Those completely govern the asymptotic behavior of this function as x goes to infinity. So that means that this is type infinity over infinity, right? So we could apply L'Hopital's rule to this, type infinity over infinity. So I do what? Limit as x goes to infinity. Differentiate, so I got 6x plus 2 over 14x. Yeah. Now, again, as x goes to infinity, I have type infinity over infinity. What can I do? I apply L'Hopital's rule a second time. So L'Hopital's rule. Over limit as x goes to infinity. Differentiate, I got what? I got 6 over 14. And that we can calculate, right? That is just 6 over 14. And it is not an accident that that simplifies to what? How
3
about?
over 7.
Yeah, 3 over 7. What's the significance of 3 and 7? Right? So, I should mention, for problems that are as simple as this, you don't have to use L'Hopital's rule. You could take a direct algebraic approach. The direct algebraic approach to this problem is just to take this and divide the top and the bottom by x squared, which gives me 3 plus 2 over x plus 1 over x squared divided by 7 minus 3 over x squared, right? If you divide the top and the bottom by x squared, you get that. But then what happens with 2 over x and 1 over x squared and minus 3 over x squared as x goes to infinity, all of those are 1 over something or some number over something really, really, really big. In other words, this goes to 0, this goes to 0, this goes to 0, and we're just left with 3 sevenths, right? So which is better, L'Hopital's rule 2 times or algebra? I think in this case, algebra